Welcome back. Now we are going to do some wrap-up. It means that we are going to use a lot of the things that we've seen during the semester, because now we are at on the top level. You see, we've done all of this during the semester. We are reaching the end now. And today we are going to be that high up in the stack. And the way to look at what we are doing now is to go back to data independence. Data independence is this principle that dates back to 1970 by Edgar Codd, which is the idea that the users should just deal with easy to understand models, like tables that have rows and columns, collections of trees. And then they should use some query language that is designed for that data model. And then it doesn't matter how it's executed physically. For example, you could have this SQL query that a user is writing, and here the elephant is PostgreSQL, could be on a PostgreSQL database, or it could be maybe on HBase with a Hive. Hive is, we didn't cover it, but it's a data warehousing layer on top of HBase that exposes SQL. So that could be on top of this. It could be on top of Spark. We saw Spark SQL, remember Spark SQL? But you see, it's the same language. That's the beauty of data independence, that you can just switch the layer or the implementation, or you could have, I don't know, a DNA. Some people did it on top of DNA, or elves in the Antarctica, right? It all works. We have a question on Zoom.
Yes. Is there a scenario where you would prefer to do only an index for, say, A instead of A and something else? Or should you always choose a maximum number of names to sort on?
So yes, there are scenarios for that. Again, it's because of the resources. You have a limited amount of memory, you have a limited amount of disk, and an index on A and B takes more space than just an index on A. And so that means that if you want to have more indices and you have constraints on the memory and on the disk, if all you need is A and you don't have a need for A and B, then you should go for just A. Does that make sense? Yes, awesome. So it's really an optimization under constraints. Memory is not free, and so it's limited. So you cannot just put all the indices that you want. There is another reason. It's just not that memory is limited. It's also that maintaining the index has a cost. When you have an index, every time you make a change to the collection, you insert a new document, you update a document, it's going to be a bit slower, because every time you make a change, it also needs to update the index. So every additional index slows down more the queries when you write back. I somehow mistakenly, it's interesting, the remark.
It says, I somehow mistakenly thought that there would be a root node per document, not per value. Then it makes sense.
A root node for in the index?
I don't really understand it.
Maybe we can talk otherwise offline if there are more questions. Yeah, I'll come back to you. Okay, so PostgreSQL, it always matters when students have questions or remarks. Apache Spark, RDDs could also be on top of RDDs, right? That you could compile SQL to RDDs. Or if the data is highly structured, even to Spark SQL or to the data frame transformations, right? Remember that these are two different APIs, right? There's the RDD API, RDD transformations, and there is the data frames API, which is different, right? And that is mapped, like you see here, to Spark SQL. So you see that's a lot of ways we can implement that, but the language is always the same. Now, we saw that for big data, for many different reasons, amongst some of the reasons are that you aggregate data over decades sometimes, and the pattern of the data changes and the schema changes. And so we are not in the beautiful world of flat and homogeneous relational tables. In the real world, you might have extra values in some objects, missing values in some others. You might have nestedness, tables in tables in tables. You might have what would be invalid values if you had a type for the column. So in the same columns, you can have different types. So in general, this is real life. And so here, you're hitting the limits of SQL. I already showed you that you can kind of deal with nestedness if you add a few dots and explode and lateral views and so on, but it's complicated. But if on top of that, the data is heterogeneous, that's even more complicated. Then you introduce variance types and so on, like in many systems. So that doesn't work anymore. We need something else. And as a reminder, this is why when you have data that is like this, so that has all of these heterogeneity and nestedness, and you try to open it in Spark using the data frame API, you will see that because you have, for example, here you have objects so for example, here you have objects and here you have a string. That's an example of this here, is invalid. As a reminder, I explained to you that what Spark is going to do is that it's going to create a column of type string, and it's going to serialize everything to a string. These are all strings. They look like objects, but it's really a serialized object to a string every time. So this is a string, and that is going to be a lot of burden for the user to deal with it, because now you have to write Python codes that attempts to parse as an object, and if it parses, it converts it to a dict. If it doesn't parse, it converts to a string, and so on. So it's a lot of additional burden to the developer, right? So we don't want that. And then in terms of nestedness, you need to introduce these lateral views. It's very difficult to process for a human being, right? To actually read the code that somebody else wrote. And what's more, if you use SQL, you have cases in which for very simple things, like for example, the email of, I cannot even tell what that does, right? But basically, this is a very long SQL query that in JSONiq that we're studying now is much shorter. That query is just looking for the top committer, right? So for every event in GitHub, we want the top committer. In SQL, you need to write that long of a query just because it doesn't fit, the data model doesn't fit. It's an impedance mismatch. And so here is one of the obvious examples. It was one by Ingo Müller, who was the head TA back then, now at Google. And he had this very, very convincing example of the benefit of a language that is tailored for nestedness. Okay, so this is what we are going to learn. The data set that we use also for the exam, we've used it a lot in past exams, comes from GitHub. And it's basically a huge collection of events like pushes, commits, and so on, everything that happens on GitHub. It's an enormous collection. In fact, it keeps getting generated every month. So every hour, in fact, you have a new tar.gz file. And so they look like this. So the first thing you see is that it's nested. That's the first thing you observed here. It's also heterogeneous because even though every event has roughly 100 attributes, in total, there's 1,300 attributes. So this is very sparse and very heterogeneous, right? They don't all have the same attributes. And if you look at the path, what do I mean with a path? I mean type is a path, commits.author is a path, repository.name is a path. So all of these values here. 10% of the paths have mixed types. So in 90% of the cases, it's going to be all integers or it's going to be all objects. But in 10% of the cases, it's going to be a mix. So at the same position in the objects, at the same position, same path, you will have values of different types. That you cannot deal with so easily with SQL. All right. So this is why we like to use these data sets for these reasons, nested and heterogeneous. And so the idea of JSONiq is exactly the same as SQL. It's a query language on the high level that is supposed to be easy to learn and to use with a clean data model and a clean design. That can run on Spark, on HBase, on Hadoop, even on MongoDB. You could make it run on MongoDB. You could make it run on PostgreSQL, like on anything that you want, thanks to data independence, right? And so what we are going to use in the course is an engine called RumbleDB. It's been developed right here at ETH by many of your predecessors, students. I will show the names shortly. And so there's a lot of master's theses and semester projects that are ongoing, and it was built for teaching. So the purpose of the engine was that we can use it to showcase exactly this. So now JSONiq, just like SQL, is a declarative language. It means it's not like Java or Python or R or you know, like a language where you have while loops, variable assignments, and so on. So it's not an imperative language; it's a declarative language. It's also a functional language. What does it mean to have a functional language? It basically means that you have building blocks, you have expressions, and every expression consumes something and spits out something. But you can model that purely mathematically, right? In many cases, without any side effect. It's like a generalized mathematics, not just addition and multiplication, but many other operations that you can do, right? So the reason it's called functional is that you could consider them to all be mathematical functions. But if the language is well designed, you do not see that these are functions. So it's not like in an API where you have the function calls and the parentheses. Here, if you have a query language, it's all hidden for the user, but we still call it functional. And finally, it is set-based. It means that what we manipulate in the language is not just one value at a time, like in Java or Python, it's one value at a time. Even a dict is one pointer, one value. But in that case, we can manipulate billions of records or billions of documents at the same time. Note that this applies to SQL too, right? It applies to both SQL and JSONiq, declarative, functional, and set-based. Who is with me? Right? Okay. And it feels like a Lego game. This is how we should view it. I'm going to give you the building blocks. There's, I think in total, there's 37 expressions. And it's just like Legos. It's the elementary Lego particles, and then you can combine them together in any way you want. RumbleDB allows you to read data from S3, from HDFS, from HTTP over the web. Of course, if it's from HTTP, you cannot parallelize. From the local file system on your machine, from Azure, blob storage, and so on. So from many places. Second, many formats. You can read text files, then you will just see strings. You can read JSON, JSON lines. You can read CSV, Avro, Parquet. It's going to be faster if you, for the reasons we discussed in the previous weeks with Parquet. Root is something used by high energy physicists working at CERN for storing the collision data, libsvm for machine learning purposes, and so on and so on. So many different formats, many different storage systems. And the vision is that it's an ideal lakehouse language. So lakehouse, I don't know if many of you heard, it was a term that was coined 3 years ago in the CIDR conference by Databricks. And the idea of a lakehouse is that it's a little bit like a combination of a warehouse and a data lake, right? Where you have high-level languages that allow you to work on top of the data. But it also works if you just drop your files in there, and at the same time, you have a high-level query language. So it's a bit of a mix between the two approaches that I've told you earlier. And one of the benefits of lakehouses is that you can update the data on the data lake. And how, I will tell you a little bit later. It's absolutely not trivial to edit data on a data lake, because normally you're just supposed to read it. There's no random access. But I'll say a few words about that. So all in all, you can see RumbleDB as a Swiss Army knife, right? It reads from many places, reads from many different formats. You can convert between the formats, just writing small queries. This is the list that I mentioned. So all the students that have been working on this, maybe you know some of them, the most recent students. Marco is actually a TA. Are you here, Marco? Maybe not today. So he's a TA in the class right now and writing his master's thesis on RumbleDB. Okay, so you see, maybe, I don't know, some of you in the future will also work on it. And the way you should see it is it's a data calculator. So just like a calculator, you can do plus, multiplication, division, powers, square roots, and so on. Generalize that to objects, arrays, and so on. So for example, 1 + 1 is JSONiq, returns 2. 3 + 2 × 4 is also JSONiq, returns 11, right? That's trivial, you're computer scientist. So 2 smaller than 5 returns true, right? So like in many languages. You have, like in many functional languages, these let clauses. Who already saw let clauses in functional languages? Some of you, right? it's not an assignment. That doesn't mean you assign 2 to I and then you see and compute I plus 1. This is not like in Java or in Python. This is really declarative. You should read that as give me $I plus 1, knowing that $I is 2. This is how to read it, right? It's a mathematical way that returns 3. That's called the flower expression. I'll come back to them. And it doesn't just manipulate numbers. You can also copy-paste JSON, any JSON, well-formed JSON. You can copy-paste it, and that's a JSONiq query. It will just return itself, right? So anything, an object, an array, anything, even complex, it just returns itself. Any JSON value, also a string, a number, a Boolean, a null, right? This also returns itself, all right? And then you have many, many more operations that you can do. For example, with dots, you can navigate. And this is also a query that you see on the top left. So foo1 dot foo returns 1, right? For whom is that obvious? Okay, that should be intuitive, right? It's really just like a calculator. Dot is just like plus, except that instead of adding, what it's doing is that it's navigating, right? But it's the same logic. If you do object-oriented programming, the dots should be normally quite intuitive. This here is an array lookup. It means that you look up the first position in this array. Why the double square brackets? I will explain. If it's a simple square bracket, it means something else, sequence lookup, but I'll come back to this. If you do an array lookup, you just need to double the square brackets. So this takes the first position in here. We start counting at 1. Many users of JSONiq will not be necessarily computer scientists. So as computer scientists, it's obvious that we start counting at 0, right? In like languages like C, C++. The reason has to do with pointer arithmetics. When you take a variable and add it to the offset of the pointer, the first should be 0 because then it's the position plus 0. It's where you are. But in fact, if you go beyond computer science and talk to people in other departments, it's not obvious at all that you start counting at 0. Right, so this is why it starts counting at 1. Okay. This is a more complex query where you have this object with a nested array that is also a JSONiq query. Dot foo, that would basically extract the array, and then the first position in the array 1, 3, plus 3, 6. Who understands this query? Right. Okay. Wonderful. This is another one where you still have this object foo, blah, 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 dot foo that takes the array. And if you have this empty square brackets here, it's basically opening the array. It's taking the array. So the array is a single item. It's a JSON array. You just open it. And when you open it, 3 values come out of it, a 3, a 4, and a 5. But that's not an array here. That's really a sequence of values, right? It's not the first time you see sequences of values. An RDD is a sequence of values. A data frame is a sequence of records, right? So that shouldn't surprise you to see sequences like that. Okay, so this is the sort of things that you can do. You can also output ranges like this. So 1 to 4 is generating a sequence of 4 numbers, 1, 2, 3, 4. This is also a flower expression, but instead of a let, it's a 4. And that's going to generate one object for each value of I between 3 and 5. So this outputs 3 for 5. And then that binds I in turn to 3 and then 4 and then 5. Then you generate these 3 objects. Who understands that query? Right? Very good. This is a more complex one. You see, it's a Lego game. You can just put anything anywhere. And here I have this query. Dot foo gets the array, pops the array open, so 3, 4, and 5, and then it iterates and does that. Who also understands that query? Very good. Oh, you're good. Very good. So then again, it's a Lego game. So you can take a for loop, not a for loop, a for clause like this, a flower, and put it inside a function call. This function returns the keys of all the objects that are in there. You can have a sequence of objects. There might be billions of objects in there. So there's billions of times you will execute that. And that returns a sequence of billions of objects. Keys is going to give you all the distinct keys in these objects and maybe just foo and bar. Okay. So the important thing is that it nests. You can really put any query inside any other query in general. This is another one where, oh yes, here with the Parquet file. So in that case, that would be opening a JSON lines file, right? That would be a JSON lines file. Even many of them, you could have an entire directory with thousands of them with the star. And here you open a Parquet file. So imagine on S3, I have somewhere some Parquet directory with plenty of Parquet files. I can open them and it's going to iterate through the records of these Parquet files. You saw that a Parquet file, in fact, contains data frames, and data frames are just valid JSON, right? So it's basically a sequence of valid JSON objects, and then we extract the keys. What is magic is that these queries look the same. The only difference is JSON versus Parquet. But there is a difference in performance with these queries when you will use them, is that in the case of reading JSON, that will be a bit slower, because that query, as you imagine, will have to read the entire data, maybe petabytes of data. Can anybody tell me why this query will happen to be almost instant? Why can I almost immediately tell you the keys in there? Yes? Exactly, we have the schema in the Parquet file. So in that case, you don't even need to look at the data to evaluate this query. You just open the Parquet file, click into the beginning of the Parquet file at the schema, and the schema will tell you the keys. For whom is that here? Right? So this is the benefit of data independence. It's the same query, but the engine can figure out ways to make it super fast just by optimizing, right? So this is what happens here. Now, before we dive into exploring, probably most of it next week, I would like to say that this is ongoing, right? It's actually been ongoing for 20 years, and I hope it will not be ongoing for too much more time, but there's all these languages. I try to keep track of them. Everybody keeps inventing languages. So JSONiq was one of the very first ones. The first one, I think, was XQuery. So XQuery was invented to navigate XML. And there was a working group in the W3C, so the same consortium that standardizes HTML, HTTP. And so it's a query language for XML. Lots of smart people from IBM, from Oracle, from Microsoft, from MarkLogic, so that sat for years and years and years every week for 2 hours discussing, trying to standardize, and they came up with the XQuery language. And then I was in the working group, and at some point, JSON was becoming more popular, and then the discussion started about how do we extend XQuery to also support JSON. And JSONiq was born then. It was roughly 2010, 2011. And so to feed the discussion, we made a proposal called JSONiq, where we added JSON objects and JSON arrays to the data model of XQuery, and we removed XML completely, right? We really replaced XML with JSON. And so then there was the discussion. The use cases for objects or arrays were actually not restricted to JSON. There's many other use cases that people had. And so what happened in the end is that we decided to keep JSONiq out there for the people who are specifically interested in JSON, because the language is very natural. But that's the story of it. The first reaction when we published it was, why do we need a query language for JSON? We already have JavaScript. But you know that JavaScript is not a query language. It's an imperative language. So it's very important to understand that nuance. So the good news is that then a lot of people realized that we actually do need a query language for JSON. So they invented query languages for JSON. And now we are in the opposite situation, that everybody keeps inventing query languages for JSON. And so what we need now, the next step, is really a consolidation. We really need people to sit together and try to agree on a common language, just like SQL for tables, that everybody would use, and then it would be fully interoperable. So we are not there yet. I hope it will happen. We have to make compromises and people talking to each other. But maybe, I don't know, in 5 years, in 10 years, maybe it happens. Maybe one of the languages establishes itself, and then all of the document stores and architecture start adopting a language. Yes?
Sorry if I missed it earlier, but what was the reason for making JSONiq 1 indexed? Not
JSONiq 1 index?
Yeah, that the indexes start with 1 and not with 0, like in most other programming languages.
Yes. So here the thinking is this. Let me try to take a step back in explaining this. The purpose of a standard in general, it's not just true for languages. It's also true, let's say, for USB. USB is a standard, right? Bluetooth is a standard. HTML is a standard. A standard is made in such a way that the technologies can interoperate with each other. That you can, if you learn it, you can use it absolutely everywhere. A standard is never going to be perfect. It's a compromise. It's people from different companies speaking with each other and reaching a compromise, right? And you make it in such a way that nobody vetoes or has a formal objection. So it means that what is even more important than the best possible design or the design that the people will like the most is the fact that the people agree on it, right? So this is the most important thing. So what I want to say with this is that starting counting at 1 or at 0, in fact, is not the most important, right? It could have been also starting at 0, that would have been just fine. What's important is that people agree. And so in the case of xQuery, the agreement came to be 1. And when we invented JSONiq, when we forked JSONiq, we did not want to reconsider discussions that had already taken place. We tried to really keep the changes minimal and take over exactly what was designed on the xQuery level and just add JSON, remove XML. The reason I'm telling you that is that it's a general lesson for you generally when you work in companies and you have to design architectures or you have to design languages. Whenever you design an API or a language, as a general principle, you should try to avoid inventing new things or reinventing the wheel. So whenever you can reuse something that already exists, then you should reuse what already exists. Let me give you an example. Imagine that you want to run a subset of Java, maybe on some mobile devices. Then the decision of what subset of Java you want to run is an arbitrary decision, right? It could be done in many different ways. If you want to do it in a good way, you should take a standard subset of Java. And that exists. That's called J2ME, mobile, the mobile edition of Java. And this is one example of when you really need to find something that is standard, that is already designed, so that you basically keep the arbitrary decisions as minimal as possible. And so to answer your question, the reason why 1 was taken as the basis for JSONiq is simply that that was what applied to the xQuery standards, right? It's a really high-level principle that I'm telling you here. There's a lot of lessons that can be learned from this. Does it make sense? Did I answer your question?
Yes, thank you.
Yeah, awesome. By the way, the way that the working group in W3C work is also really nice in terms of communication, because the culture in the working group was that when somebody was speaking, everybody would just listen and let them finish until they're done speaking. And people would take turns and everybody would speak like for 5 minutes uninterrupted. Then you basically listen to each other. It's really a very organized and a great way of moving forward. But of course, it takes years in order to reach a recommendation. All right, so that was a bit of a parenthesis for 5 minutes on a meta level, but there's a lot of lessons here that you can maybe use later in employments. All right. So I'm totally unable to tell you which language is going to win. Maybe it's going to be a mixture. It doesn't really matter which one wins, right? They all follow more or less the same principles. If I teach you one, so JSONiq, then you will see that you can learn any other quite easily. And so if one day there is a standard that everybody adopts, then it will be easy for you to learn it. In fact, I have an example of that. Who saw the Google SQL pipes announcement on social media? So they extended SQL using pipes. In fact, that exactly corresponds to the flower expressions that are in JSONiq. So the students who learned JSONiq in previous lectures when Google SQL pipes were released, that was very easy for them to learn it. All right, we'll have maybe not much time left, but maybe I still have time to tell you about the data model in JSONiq. So you already know that JSON has 6 building blocks, right? There's objects, there's arrays, there's strings, there's numbers, there's booleans, and there's null, 6 of them. So in JSONiq, the data model says that everything is a sequence of items. Everything that comes into an expression or comes out of an expression, that's a sequence of items. Sequences of items are completely flat and they are heterogeneous, meaning that you can have a sequence that contains plenty of things. You could have a string, an integer, an array. You can completely mix them. That's absolutely not a problem. So it's heterogeneous. It's denormalized in the sense that you can also have objects and arrays in there. So you can have structured items. Also, a sequence of one item is the same thing as that item. So for the purpose of thinking, if you say I have a string, it's the same thing as saying I have one string. It's the same thing as saying that I have a sequence of one string. For whom is that clear? Right? So a sequence of items is the same thing as one single item, and it's flat. If you attempt to nest them, they will never nest. If you take a sequence of 2, then comma another sequence, it's just a sequence of 3, right? That doesn't nest. We'll see that if you want to nest, you should use arrays, right? But sequences, they are flat. And this is the empty sequence. It's the sequence that has nothing in it, right? Just the empty sequence. If you want to map it to things you've already seen, then just think of an RDD, right? An RDD of whatever. Then that's what it's corresponding to in terms of a sequence. You can even have heterogeneous RDDs, right? If you have an RDD with a polymorphic type, then you can also actually have heterogeneous RDDs. Okay, so I'm going to stop here. So remember, because I'm going to repeat this many times, everything in JSONiq is a sequence of items. And by the way, that also comes from xQuery. In xQuery, everything is a sequence of items. The only difference is that in xQuery, you would have XML elements, XML attributes as items. In JSONiq, instead, you have JSON objects, JSON arrays, and atomics as items, right? So atomic values, objects, arrays can be items. Functions, not in this course. I'm just leaving them aside. Atomics, objects, and arrays. So I'm going to stop here. It's exactly the right time because it's ringing. So we'll continue next week. I'll see you, and then we'll explore the whole language JSONiq in 2 hours. Thank you very much, and see you.